Well, in this lecture, we're going to talk about one particular approach for inverting the Z transform, and that involves the use of partial fraction expansions. The partial fraction expansion technique applies to inversion of Z transforms that can be expressed as rational functions of Z inverse. And the basic idea is that we're going to break x of z into elementary forms that can be inverted by inspection. So let's suppose I have x of z in this form here. It's a rational function in z inverse. 1 plus 2z inverse plus z to the minus 2 divided by 1 minus 3 halves z inverse plus 1 half z to the minus 2. We'll assume our region of convergence is the magnitude of z greater than 1. Well, if I break this up using the technique of partial fraction expansions, I can write this as 8 over 1 minus z inverse minus 9 over 1 minus 1 half z inverse plus 2. And the point is that each of these terms is very easy to invert because we've seen these kind of z transforms before. We've already derived them. So the partial fraction expansion is a process of undoing the combination of terms over a common denominator. Here we have a common denominator on the left, and here we've undone that. We put things over their own individual terms, and that's how we will approach our inversion of Z transforms. So we're going to start off with x of z, and we're going to assume that x of z is written in powers of Z inverse. If it's not in powers of Z inverse, then we would convert it to a power of Z inverse before beginning. So then we consider the order of the numerator polynomial relative to the order of the denominator polynomial. If the order of the numerator is greater than or equal to the order of the denominator, we have to use long division to write out x of z in terms of some constant terms or terms involving Z inverse, and then a rational function where the order of the numerator is less than the order of the denominator. So the second step is to factor the denominator as a product of first order terms. We're going to write the denominator in terms of the poles. So if dk is a pole, you can see that we've done the factorization here by writing the product k equals 1 to n of 1 minus dk z inverse, and we've pulled out the a0 term from in front so that the z to the 0 power will have coefficient 1 when I multiply this out here, and then consequently on the left, a0 would be the coefficient associated with z to the 0. Then in the third step, once we have this denominator expressed in terms of the product of poles, we're going to write it as a sum of first order terms. And the case I've written up here, where we write it as a sum from k equals 1 to n of some coefficient ak divided by 1 minus dkz inverse, this particular form assumes that the dk are distinct. In other words, none of the poles are repeated. Well, it turns out that you can also do this. It's a little more complicated if there are repeated roots, but if d sub I is repeated r times, then there's going to be r terms in the partial fraction expansion associated with that particular pole, and they take the form of a coefficient in the numerator, and then in the denominator we have 1 minus di z inverse raised to the lth power, where L goes from 1 to r. So once I've expressed my original term after long division in terms of a sum of first order terms, it's a simple matter to do the inversion, because each of these first order terms we know how to invert. We know that ak over 1 minus dk z inverse either goes to a causal term looking like ak times dk to the nth power u of n, and that happens if the region of convergence is such that it includes values of z whose magnitude are greater than the magnitude of the pole. On the other hand, if the region of convergence includes values of z that are inside the magnitude of the pole, then we'd get the non-causal term, negative ak dk to the n u of negative n minus 1. And you get the same sort of behavior for the case of repeated roots. It's a little more complicated. If I have power L in the denominator, 1 minus dk z inverse to the Lth power, then I get this term where I have n plus 1 dot 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 times n plus L minus 1 divided by L minus 1 factorial d to the n u of n. We can invert each of the terms, and therefore we have our inverse z transform. So let's do an example here where I've got x of z given by 1 minus z inverse minus z to the minus 2 over 1 minus 1 half z inverse times 1 minus 2 z inverse times 1 minus z inverse. And we'll assume our region of convergence is the ring magnitude of z between 1 and 2. Well, in this particular case, x of z is already expressed in terms of powers of z inverse, and you'll notice that the numerator polynomial is order m equals 2, whereas the denominator polynomial, which happens to be factored already, would have order n equals 3. So in this case, we don't need to do long division, and we can proceed to the next step, which is also taken care of for us because the denominator has already been factored. So we'll move directly to the partial fraction expansion step, and in this case I'm going to write x of z as a coefficient a1 divided by the first pole, 1 minus 1 half z inverse, plus a coefficient a2 divided by the second pole, 1 minus 2 z inverse, and then a coefficient a3 divided by the third pole, 1 minus z inverse. So then we're going to solve for a1, a2, and a3 so that this sum expansion here is equal to the original x of z. And one way to do that is to put these terms on the right-hand side back over a common denominator and then set different powers of z on the left-hand side equal to the corresponding power of z involving the coefficients on the right-hand side. And that's in general going to lead us to a system of linear equations. A simpler approach is to isolate each of the terms. And if I take x of z and I multiply by the denominator involving a1, in other words 1 minus 1 half z inverse, and I evaluate at values of z where this factor that I multiplied by goes to 0, then I'll isolate a1. Because when I multiply by this term, I have it on the left times x of z, and then on the right, I have a2 times 1 minus 1 half z inverse and a3 times 1 minus 1 half z inverse. And when I evaluate that at the values of z for which this goes to 0, the a2 and the a3 drop out. And of course, when I multiply by this times xz, I'm just canceling it out of the original denominator. And in this case, 1 minus 1 half z inverse goes to 0 when z inverse equals 2. So I'm going to obtain x1 or a1. I'm going to obtain a1 as 1 minus z inverse plus z to the minus 2. That's my numerator of x of z. And then I have the two remaining terms in the denominator because there was a cancellation. And I'll evaluate all these at z inverse equals 2, and that gives me 1 minus 2 plus 4 divided by 1 minus 4 times 1 minus 2, and this comes out to be exactly 1. So that's a1. We can repeat the same process for a2 and a3, and we find out that a2 becomes equal to 2 if you go through the algebra, and a3 becomes equal to minus 2. So I've now expanded my x of z up top in terms of a sum of 3 first-order terms, each of which I know the inverse z transform for. The final step is very straightforward. I'm going to invert each of these terms using my region of convergence information. Now I've sketched the region of convergence here. Recall it was the ring where the magnitude of z was between 1 and 2. And I've also located the poles. There's one at a half, there's one at 1, and there's another pole at 2. So the pole at 1 and at 2 are bounding the region of convergence. So the first term, 1 minus 1 half z inverse, the pole is inside of the region of convergence. So that means that I'm going to have the causal term for the inverse z transform. And that just becomes 1 half to the nth power u of n. The second term, 2, divided by 1 minus 2z inverse has a pole at z equals 2, and this pole is outside of the region of convergence. And so I'm going to have the non-causal inverse Z transform, and I get minus 2 times 2 to the n u of minus n minus 1. And then the third term, which is minus 2 divided by 1 minus Z inverse, this particular pole at z equals 1 is inside of the region of convergence, so I'm going to have the causal expansion, which just looks like 2 u of n. Now I could have written 1 raised to the nth power here, but there's no need. It's just 2 u of n. So I put these three together, and I conclude that x of n is 1/2 to the n u of n minus 2 times 2 to the n u of minus n minus 1 minus 2 u of n. We'll do another example here with a few more of the steps required. And in this case, I'm giving you x of z is z cubed minus 10z squared minus 4z plus 4 divided by 2z cubed minus 2z squared minus 4z. And we'll have a region of convergence, magnitude of z less than 1. Well, you'll notice that x of z here is given in powers of z. So we're going to write it in terms of powers of z inverse. And we'll do that by dividing both the numerator and denominator by z cubed. And therefore I obtain x of z is 1 minus 10z inverse minus 4z to the minus 2 plus 4z to the minus 3. And in the denominator I have 2 minus 2z inverse minus 4z to the minus 2. So now we can begin our procedure that we have x of z written in terms of powers of z inverse. And our next step is based on comparing the order of the numerator polynomial to the order of the denominator polynomial. And what you see here is that the numerator polynomial has order m equals 3, but the denominator polynomial has order n equals 2. So the order of the denominator is less than the order of the numerator, and we need to use long division to reduce this to a polynomial where the order of the numerator is less than that of the denominator. So I'm going to divide negative 4z to the minus 2 minus 2z inverse plus 2 into 4z to the minus 3 minus 4z to the minus 2 plus 10z minus 1 plus 1. So the first term, if I want to cancel out this 4z to the minus 3 term, I can do that by multiplying negative 4z to the minus 2 by negative z inverse. When I multiply this through here, I have 4z to the minus 3. Now I have plus 2z to the minus 2 minus 2z inverse. Do the subtraction, and we have negative 6z to the minus 2 minus 8z to the minus 1 plus 1. Now I could put this over the denominator, and at this point we'd see that the order of the denominator, which is 2, is equal to the order of what would be in the numerator, which is also 2. So I need to divide again to reduce the order further. So I want to divide negative 4z minus 2z inverse plus 2 into this term here. And to cancel out the negative 6z to the minus 2, I need to multiply this coefficient, negative 4z to the minus 2, by 3/2. And if I multiply this entire polynomial here by 3/2, I obtain negative 6z to the minus 2 minus 3z inverse plus 3. When I subtract these two, I get negative 5z inverse minus 2. Now at this point, the remainder term is indeed of order less than the denominator order, because the denominator order was order 2. So I can write x of z as negative z inverse plus 3/2. That's the result of my long division, plus the remainder, negative 5z inverse minus 2, divided by my original denominator, 2 minus 2z inverse minus 4z to the minus 2. So at this point, we can do the partial fraction expansion of our remaining fraction in x of z. So we'll first factor the denominator. We can pull the 2 out and write this as 2 times the quantity 1 plus z inverse times 1 minus 2z inverse. Now we'll expand this term, having factored it, in terms of a sum a1 over 1 plus z inverse plus a2 over 1 minus 2z inverse. And I've moved the 2 that was in the denominator down here up into the numerator for this expansion. So a1, again, we'll obtain a1 by multiplying on the left and right by 1 plus z inverse, and then evaluating at z inverse equals minus 1. And that gives us this expression here that I've written out. We have negative 5 halves, z the minus 1, divided by 1 minus 2z inverse, evaluated at z inverse equals negative 1, and that comes out to 1 half. And similarly, we'll do the same sort of procedure to isolate a2 and solve for it. We find that a2 becomes equal to negative 3 halves. So after my partial fraction expansion, I can write out x of z as negative z inverse plus 3 halves plus 1 half over 1 plus z inverse minus 3 halves over 1 minus 2z inverse. And this applies for a region of convergence, the magnitude of z less than 1. So we've got x of z in terms of very simple terms, all of which we can invert by inspection, and we'll do that in our next step. So we have to decide with each of these terms whether to use the causal inverse Z transform or the non-causal one. That is, whether the signal is going to extend off to the right or it's going to go to the left. So first we're going to graph the poles and zeros in the region of convergence. And in this case, you can see that the region of convergence is a circle of radius 1, and it's inside of that region of circle of radius 1. So both poles have radius greater than the region of convergence. So that tells us we're going to use the non-causal or the left-sided inverse Z transforms. So this first term has a pole at Z equals 2, and that's going to then convert to 3 halves, 2 to the n, u of negative n minus 1. And you'll note that we've changed the sign out here from minus to plus. Then we go to the second term, and again, this is left-sided, so we're going to change the sign. We now have minus 1 half, negative 1 raised to the nth power, because the pole is at negative 1, u of negative n minus 1. And then these two remaining terms are the form of a power series. We see that 3 halves is associated with z to the 0 power, so we know that occurs at n equals 0. We have 3 halves delta of n. Then the other term is associated with the power z to the minus 1, so that's going to occur at time n equals 1. We have negative delta of n minus 1. So there's our full inverse z transform. In closing, I want to make a couple of remarks, and one is that if x of z has real coefficients, then the poles are going to occur in complex conjugate pairs, because the roots of polynomials with real coefficients occur in conjugate pairs. So for example, if we have a pair of conjugate poles, d1 and d2, then d1 has to be equal to d2 conjugate. In this case, you also are going to have complex coefficients, but they're going to be in complex conjugate pairs as well. So if I say that I have a1 over 1 minus d1 z inverse, then over the term with the pole d2, which is the conjugate of d1, I must have a1 conjugate. And to solve this one, it's simplest to expand a1 in terms of its real and imaginary parts. So I've got the real part plus j times the imaginary part, and then in terms of d2, I have the real part minus j times the imaginary part, because this is the conjugate. The algebra gets a little more complicated, but nevertheless the method works exactly the same. One can use information other than the ROC to do the inversion. For example, if we know ahead of time that we're interested in causal signals, then of course we're going to take the right-sided inverse Z transforms. Or if we know that our signals are stable, which means that they're absolutely summable, that tells us that the ROC includes the circle magnitude of Z equals 1. And in that case, we can also determine where the pole is relative to that ROC and do the inverse accordingly. Now, this whole procedure that we've done has been in terms of expansion using Z inverse. It turns out you could also do this in terms of the powers of Z, because recall that we had Z over Z minus d, the inverse z transform, let's pick the causal one, it's going to be d to the n u of n. But I find that the algebra is a little bit simpler to work in terms of z inverse because we have to have these constant terms in the numerator. But nevertheless, it can be done that way as well, if you wish.